Hi, it's Mr. Mac. Welcome to Electrostatics, a topic in Module 4 of Year 11 Physics. As you can see, our inquiry question is, how do charged objects interact with other charged objects and with neutral objects? What we're going to be doing is learning to describe and analyze qualitatively and quantitatively charged objects and electric fields. At the end of this, we'll be able to quantitatively analyze interactions between charges and their motion in an electric field. As we know, matter is made up of atoms. Atoms have a nucleus of neutrons and protons surrounded by electrons. Each proton has a mass of 1 and a positive charge. Each neutron has a mass of 1, but no charge. And each electron has very negligible mass and has a negative charge. So who discovered electric charges? Thales of Miletus in Greece, around about 636 to 546 BC, observed that amber rubbed with wood attracts pieces of fluff and fragments of straw. The amber, which is a naturally occurring rock from ancient resin, had become electrically charged. The word electricity comes from the Greek word for amber. In 1600, William Gilbert from England found that many substances rubbed together attract other substances. In 1733, Charles Dufay from France discovered two different types of electricity, which he called vitreous electricity, when glass is rubbed with silk, and resinous electricity, when amber is rubbed with fur. After observing and doing electricity experiments in 1746, the famous Benjamin Franklin from America renamed vitreous charge as positive charge and resinous electricity as negative charge. Why he used this positive and negative convention is not known, but since then it has never been changed. Nowadays we say that when a glass rod or a perspex rod is rubbed with a silk cloth, electrons are lost from the atoms in the glass or perspex and transferred to the atoms in the silk cloth, leaving the glass rod with more positive charge than negative charge, and so it has a net positive charge. The convention is that a glass rod or a perspex rod rubbed with a silk cloth has a net positive electrical charge. So we can see from this simple experiment that a perspex rod rubbed with silk becomes positively charged, and also an ebonite rod rubbed with wool becomes negatively charged. The charge on one electron is negative 1.602 times 10 to the negative 19 coulombs. Electrons are in orbit around the positively charged nucleus. This is because positive and negative charges attract each other with a pulling force. Similar charges, positive and positive, or negative and negative, repel each other with a pushing force. Let's have a look at worked example 1. A body has a charge of 2.3 microcoulombs. Does it have an excess or deficiency of electrons? Well, how many electrons are excess or deficient? Well, since the body is positively charged, positive 2.3 microcoulombs, it has a deficiency of negatively charged electrons. Remember that the charge on one electron, QE, equals negative 1.602 times 10 to the negative 19 coulombs. You can find that number on your data sheet. The number of deficient electrons, N, is given by the formula N equals Q over QE. Q is the charge on the body, QE is the charge on one electron, which equals 2.3 times 10 to the negative 6 over negative 1.602 times 10 to the negative 19. That equals, using calculator, negative 1.44 times 10 to the 15 electrons. Remember, deficient means the sign is opposite. So, what does that mean? The body is deficient of 1.44 quadrillion electrons. Electric fields. When you have a charge or a collection of charges, this influences the region around it, causing an electric field. The electric field from a positive charge points away from the charge. The electric field from a negative charge points toward the charge. Like the electric force, the electric field E is a vector. An electric field can be visualized on paper by drawing lines of force, or field lines, which give an indication of both the size and the strength of the field. The field lines start on positive charges and end on negative charges, and the direction of the field line at a point tells you what direction the force experienced by a charge will be if the charge is placed at that point. If the electric field at a particular point is known, the force a charge Q experiences when it is placed at that point is given by F equals QE. If Q is positive, the force is in the same direction as the field. If Q is negative, the force is in the opposite direction as the field. Let's look at electric fields between charged objects. The fields that you would get for 4 important arrangements are what we're going to look at. Firstly, 2 unlike charges, a positive and a negative, form an attraction. Secondly, 2 like charges, a positive and a positive, or a negative and a negative, have a repulsion. Thirdly, a charge and an oppositely charged plate form a complex arrangement of field lines. Notice the field lines go from positive to negative. And fourthly, when you have 2 oppositely charged plates, it forms a uniform electric field with the arrows going from positive to negative. Let's look at worked example 2. A particle with an electric charge of Q equals 7.45 times 10 to the negative 4 coulombs is placed in an electric field, and a force of 8.75 times 10 to the negative 2 newtons acts on the particle. What is the field strength at that point? Well, the first step is data. Q, the charge, equals 7.45 times 10 to the negative 4 coulombs. F, the force, which is a vector, equals 8.75 times 10 to the negative 2 newtons. The formula that we use, E equals F on Q, which equals 8.75 times 10 to the negative 2 divided by 7.45 times 10 to the negative 4. Now this results in a very long number, 117.44966442, and keeps on going. But we'll write down 117 newtons per coulomb, correct to 3 significant figures. And the reason is the question gave the 2 data points in 3 significant figures.